The final thing we want to do is show that Goodstein's theorem is hard to prove. We've already seen a proof of Goodstein's theorem, so we mean something more technical. We want to show that P&O arithmetic cannot prove Goodstein's theorem. P&O arithmetic is a formal theory of the natural numbers. We'll give a more rigorous statement of it later, but basically, P&O arithmetic contains some axioms that state the basic properties of the natural numbers, like 0 is the only number which is not the successor of some other number. Adding 0 doesn't change a number, and so on. And then P&O arithmetic has the axiom scheme of induction. For each formula phi, if we know the base case, phi of 0, and the inductive case, whenever phi holds of x, phi holds of the successor of x, then phi must be true of every x. So P&O arithmetic is the axioms that say arithmetic works the way we're used to, and we can do proofs by induction. And if you write down what should the axioms of the natural numbers be, this is a pretty good list of standard facts we use. P&O arithmetic is often seen as a sort of a benchmark. It contains everything we expect to use in an ordinary proof about numbers. And in fact, most theorems about the natural numbers, other than ones cooked up by logicians specifically to be difficult to prove, can be proven in P&O arithmetic. That's not obvious. That's an empirical fact people have put a lot of work into verifying, and it's most, not all theorems. But most typical theorems can be proven in P&O arithmetic. So when we show that P&O arithmetic can't prove Goodstein's theorem, we really are showing that any proof of Goodstein's theorem somehow goes beyond the most common techniques used in mathematical proofs about the natural numbers. As all this discussion about formulas suggests, we're going to be working with formulas of first-order logic in the language of arithmetic. That would be a whole topic of its own to introduce fully in detail from scratch. In the rest of this video, I'll just give a quick recap about the exact language we're using and how we'll be thinking about first-order logic here. The building blocks of first-order logic are terms and formulas. Terms, in the language of arithmetic, are formal expressions which represent natural numbers. 0 is a term. And then terms can be built using function symbols. So the successor of 0 is a term. And we can also build terms using addition and multiplication. It's convenient and harmless for what we're doing to allow lots of other function symbols in our terms. For instance, we might as well include exponentiation. In fact, it's specifically convenient to include the function symbol for the Goodstein sequence. That is, the function symbol gi of n, which has two inputs, I and n, and its output is the ith term of the Goodstein sequence starting with n. So we can go ahead and write things like g7 of 12 and treat that as a term, and nothing will go wrong. There is some limit to what we can add. For instance, we certainly wouldn't want to include the Goodstein function as a term. When we say gi of n is a term, we're implying that the number gi of n exists. The whole point is to prove that g of n exists, so if we add that as a term, we'd be treating Goodstein's theorem as an axiom, so of course it would be provable. There's a more formal way to say which functions it's okay to include as terms. Ultimately, it will fall out of our proof. We're going to prove we can't prove Goodstein's theorem in P&O arithmetic, and we'll see that what we use is that our function symbols represent functions which are bounded by one of those fast-growing functions h alpha. And somewhere in the proof we will use that assumption. But as long as our terms represent functions that grow not too quickly, we'll be fine. One last thing about terms, they can also include variables. So the variables x, y, and z are terms, and so things we build from them like x plus y, or 0 plus x plus y plus z, or g of the successor of x of y plus z plus 300 are also terms. The other building block we need are formulas. The basic formulas are the atomic formulas, the ones not built from smaller formulas. There are only two kinds in the language of arithmetic, equalities and inequalities. So when we have two terms, there are two questions we can ask. Are these terms equal, or is one less than the other? So a typical atomic formula might be 1 plus 1 equals 2, or g3 of 8 is greater than 12, or 1 times 3 is greater than 100. Formulas can be true or false, or they can have variables like 1 plus x equals 3, or gx of y is greater than 7. From the atomic formulas, we can build up some more complicated formulas. We have three logical connectives, not, and or. The convention in logic is to write negation like this, like the subtraction symbol with this extra tick at the end. So if phi is a formula, we write not phi to mean its negation. We write and, the conjunction of two formulas, using this symbol, the wedge. And we write or, the disjunction, using this symbol, the upside down wedge. So when we write this, it means phi is true and also psi is true. And when we write this, it means either phi is true or psi is true, or maybe both. Often people include an implication symbol, and it's going to be convenient for us to have as few symbols as possible. So where we would normally write phi implies psi, we'll instead write the negation of phi or psi. Finally, we have the quantifiers. We write the upside down A to mean for every, and the backwards E to mean there exists. So we write this to mean for every x, phi is true of x, and we write this to mean there is some x, so that phi is true of x. Once we start writing formulas with quantifiers, it's natural to want to think about the formula you get when you replace the variable x with a particular term. I'm going to use the following very explicit notation. We write phi with this x maps to 4 to mean take the formula phi and replace the variable x with 4. So phi is 2 to the x is less than 17. Phi of x maps to 2 is 2 to the 2 is less than 17. And phi of x maps to 8 is 2 to the 8 is less than 17. So when we say for all x phi is true, that should mean phi holds when you replace x with 1, and when you replace x with 2, and when you replace x with 0, and when you replace x with 3 billion, and so on. In particular, we can state Goodstein's theorem in this language. Goodstein's theorem says for every x, there is some y, so that gy of x equals 0. For every x, the Goodstein sequence starting with x eventually terminates. So our goal is to prove we can't prove this statement in P&O arithmetic. I should point out, Goodstein's theorem is an example of a special kind of formula. It's an example of a sentence. A sentence is a formula with no free variables. There may be variables in the formula, but they have all been bound by quantifiers. A sentence is a statement that could be plausibly true or false. Whereas if there are free variables, then the truth might depend on the value of those variables. So we'll often be particularly concerned with sentences. We're now ready to list our axioms more precisely. We'll actually allow more axioms than just P&O arithmetic, and even with these additional axioms, we still won't be able to prove Goodstein's theorem. I'll call our system of axioms PA+. That's not a standard name, it's just a reminder we're working in P&O arithmetic plus a little extra. The reason we're allowing extra axioms is because we have all those extra function symbols. We don't want to have to worry about figuring out exactly what axioms they all need. We will just go ahead and throw in every true universal fact about the natural numbers. Universal means the only quantifiers are some universal quantifiers in the front. So we have axioms like for all x, x plus 0 equals x, because this is true in the natural numbers for every x. We can have multiple quantifiers like for every x, for every y, x equals y, or x is less than y, or y is less than x. We can have none, like 2 to the 4 is less than 17. This is a true atomic fact, so we'll let it be an axiom. This is actually a lot of axioms, but having too many axioms is fine. We're going to prove that even with this extra help, we can't prove Goodstein's theorem. What's important is we have at least everything P&O arithmetic has, and this list of all true universal axioms includes all the usual axioms of P&O arithmetic for defining 0 and successor and plus and times. We still need the induction axioms, and because we don't have implication, we'll just state them a little differently. The induction axiom in PA+ says either phi is not true of 0, or there is some x violating the inductive case. There is an x where phi is true of x, but is not true at the successor of x, or for every x, phi is true of x. This is exactly the usual induction axiom, but we're not using the implication symbol, so we're using ors and we're negating things appropriately instead. All right, that's the full definition of PA+. It's an empirical fact that most theorems about the natural numbers that appear in mathematics can be proven in PA+. That means using only the axioms of PA+, and the standard rules of first-order logic, the rules for working with connectives and quantifiers, you can derive most theorems of ordinary mathematics, as long as you can state them in this language. So if you open a journal in mathematics and you see a result in number theory that's just a statement about the natural numbers, you could probably, maybe with a lot of work, prove it in PA+ in a formal way. If you open a journal and read a theorem about functional analysis, it's not a statement about the natural numbers, and you probably couldn't state it in the language of arithmetic, never mind whether it can be proven from these axioms. But you cannot prove Goodstein's theorem using the axioms of PA+, and the goal of this last group of videos is to prove that.